Hello. So in this video we will be starting a new module, that is a new syllabus, thyristorized AC motor drive. So as you could easily understand that in AC motor we have talked of two machines mainly. In AC motor we have talked of two machines, mainly three-phase IM and synchronous machine. So we will be concentrating on these two. So out of these two, we will be starting with this three-phase induction motor. So since it's an AC machine, so it can be easily represented as this is the stator of the induction machine, this one is the rotor, this one is the shaft, moving with the speed omega r. There is a three-phase connection to the induction machine. Now this three-phase connection will be coming through an inverter that is made up of thyristor. So on the left hand side here in this part we will get an AC. Sorry, in this side this one is AC and this side this one is DC. So depending on this DC source, two situations can be occurring. One is that you can connect a capacitor over here. Then another thing is that you can connect an inductor over here. So which one you will be going to connect over here, that depends on the application. If you are connecting capacitor over here, then it is a VSI, okay, a voltage source inverter, and if you are connecting an inductor over here, then it is a CSI, current source inverter. Okay, and in this side you are having a diode to make the AC to DC. So this is effectively a thyristorized AC motor drive in open loop. So when we are talking of this three-phase induction motor, we will be talking of the performance of this three-phase induction motor. A quick recapitulation of what you have learned already in my class. Okay, so the speed torque characteristics. This one will be extended in the other part also. And this one extended in this part. Okay. This is this synchronous speed, omega s. This is with respect to omega, this is speed, and this is torque. Okay. So this zone is the motoring zone. As you know, this one is the regenerative zone, and this zone this is plugging, is omega s, and here the speed is 0. Here the speed is more than omega s, and here the speed is less than 0 in opposite direction. Less than 0 means in opposite direction there is speed. So in motoring zone, your air gap field and the rotor speed, both air gap field direction and rotor field direction, rotor speed direction, both are in same direction. Both are same. This is the speed of the magnetic field, speed and direction of the magnetic field. This is speed and direction of the rotor. In regenerative mode also, the magnetic field direction and the speed both are same. As you could easily understand that in this zone the synchronous speed, that is the magnetic field direction, magnetic field speed is quite lesser than the rotor speed, otherwise it will not go to the regenerative mode. In this plugging mode, the magnetic field direction and the speed both are opposite. That is, from here on the motor is moving to the opposite direction. This point is the starting torque. TST. This one is the maximum or breakdown torque. Okay, so this is the speed torque characteristic of an induction motor, what you have learned earlier. Now there you have learned of three things. This is page 1. You have learned of three things. One is the speed torque characteristics when the voltage is varied. Voltage means here stator voltage. Voltage is varied. Number 2 is that when there is a variation of R2 dash or the rotor resistance with respect to X2 dash, this one is variable. This one effectively means that you have got some R dash resistance, which is the combination of R2 dash, that means the resistance which is already in the motor plus some external resistance, this total. And the third one is variation of frequency, that is frequency is variable. So you can get back to your earlier notes that whenever there is the stator voltage variation, so you will be getting curve like this. And this is the synchronous speed, this is with respect to speed, and this is torque, where this one is the stator voltage Vs, rated stator voltage. This one is something less than the rated stator voltage, and this one is much less, 0.3 Vs. So this way the curve goes down. Okay. In the second case, when you have this rotor resistance is increased with respect to this impedance. There the graph is like so what I can find from your earlier notes that I have explained this one with alpha. There's some variable called alpha which I have defined as this one. So since both this rotor resistance and this rotor x2 dash, this part also, this is both these values are referred to stator, so you can easily do this one in this way. Okay. Torque, this is omega. So here you can see that the maximum torque, that one varies, and also the starting torque, that one varies. So in this case the maximum torque remains same. This is from the earlier notes. I am just taking it down from my earlier notes only. Okay, the maximum torque remains same, that is this is T max. What varies is the starting torque. Okay, so this is omega s. Okay. So this one is where alpha is less than 1. This one is when alpha is greater than 1. And this one is when alpha equal to 1. Okay. So what does that mean? This means that when you go on increasing the resistance, when you go on increasing this rotor resistance, and the curve shifts this direction. The curve shifts in this direction, that is, this alpha is increased. And you could very well see that where alpha is less than 1, that means it is the starting torque is low, the starting torque is high for alpha equal to 1. For alpha is greater than 1, the starting torque increases, but the maximum torque, that remains same, but the slip at which the maximum torque occurs, that varies. So this is number 2. And number 3, you have to keep in mind 2-3 important things. One is that you are varying the frequency. You are varying the frequency, right? So when you are varying the frequency, you have to keep the flux constant. This one should be kept constant. So when you want to keep this flux constant, this E by F ratio, that has to be kept constant. But this E, you don't have any access to this E. However, we can easily prove that the terminal voltage V is almost equal to E. So what we keep constant is this V. So in normal way, this is called V by F control. This one has to be kept constant. Okay. So when you draw this speed torque characteristics, this one is also from the previous teaching in my class. That at this point, this one is the omega S point. That is the synchronous speed. Okay. Here you see that both the starting torque varies, both the maximum torque varies. However, this maximum torque does not vary until it reaches the base speed, that is omega s. After that, the maximum torque decreases. Okay. So this is only one case where this omega s, this point is changeable. Why? Because you are changing the frequency. That means you are checking the supply frequency effectively. So supply frequency effectively means that omega s, you are changing the synchronous speed. So this is the speed torque characteristics of induction motor. So out of what we have learned till now, we can summarize this one. Into 2-3 parts. Into 2-3 parts, that is so this is the torque, this is the speed. Here we are taking something, that is the base speed omega s. So till here the flux is constant. So this is the flux line. This is effectively equal to psi m, and which is a function of Im, or magnetizing current, right? Next, we will be talking of some voltage, V, stator voltage. So stator voltage should come from here. But in actual case, it is started above the zero line. This will be explained later, but it is started above the zero line. So this is effectively stator drop compensation. This is the stator voltage Vs. Okay. After some part that if we are having some winding in the machine, so that winding can sustain a certain amount of voltage above which it cannot sustain. So the stator voltage has a definite value till which it can reach. After that, if you increase this voltage, the windings of the machine will be burnt out. So after this value, it cannot move. Now this voltage is designed in such a way that it corresponds to the synchronous speed of the machine. Okay. After that, it will become steady in this zone. I will be explaining this zone later. Just for the time being, why it will be reaching maximum here is explained. Now coming to the stator current, right? So we are taking that the stator current is rated from previous only. Okay, and this stator current is taken as a rated stator current is applied throughout the motor, and this value has also have some definite value before what it cannot go. The same problem is there, that while designing, the winding of the machine is designed in such a way that it can sustain a certain amount of value only. So suppose we have this, we are maintaining this current to some definite value more than this speed, the synchronous speed, torque. Okay, so this is the constant torque zone. Why it is a constant torque zone? Because if you see the torque equation, you will be finding out that torque is equal to K is a function of I2 dash square R2 dash by S. So since the stator current is not changing, that means the corresponding I2 dash is also not changing. Here, if the magnetizing current is kept same, what is IS? IS is actually the vector sum of Im plus I2 dash. So till this zone, if these two currents are not changing, that means IS is also not changing. Sorry, if IS and Im is not changing, that means I2 dash is also not changing. If I2 dash is not changing, that means the torque that is also not changing. That means here we are getting a constant torque. Was torque. Okay. Now what will happen next? In the next case, we will be decreasing this flux current, decreasing this magnetizing current, or decreasing this flux. Because why? Because when you have to go to a speed above the synchronous speed, you have to decrease this flux. This is the same conception that you have learned in DC machine. That you go to a speed above the rated speed, you have to decrease the flux. Right? So when this flux decreases, but still this stator current is kept constant, then this voltage will be fixed from here only, because you cannot increase this voltage. It has reached the maximum value. If you increase this voltage, the winding will burn out, right? So here what will happen to this flask, that this one will decrease. This decrease is directly proportional to 1 by f, 1 by frequency. This you can easily calculate from equations, right? And after this, what happens? After this, now you have decreased this magnetizing current. From here on, you are decreasing the stator current also, because since the magnetizing current has decreased, so this one has decreased. Now this one also has some capability of sustaining, of taking the current. Why? Because your rotor windings are also of that form. While designing that, you have kept that maximum amount of rotor current can go. So you have decreasing this current, this stator current. Correct. So now what will happen? This torque will be decreased further, right? This is proportional to 1 by f square. Okay. So what we could see is that this zone is a constant torque zone, this zone, that is TE, this is constant. This zone is constant power zone. Power is constant. So this one you can easily find it out, that why this is constant torque and this is constant power, because here you see that power is equal to what? In this part, your Vs and Is both are same, right? So this is effectively power equal to Vi cos phi. Input power and input power minus losses. Losses are almost constant in an induction machine during an operation. It depends on frequency, but not too much. Okay, only the core loss and hysteresis loss, all those losses. Main depends on frequency. Mainly that I square are losses that does not depend on frequency. So here you are getting a constant power zone. Power is constant. That is T E omega m, omega R rather. This one is constant. Okay, and in this zone you can find it out that here this Te omega R whole square, this is equal to constant. So this zone, the third zone, that is from here onwards, this side, This zone is mainly used for high-speed electric vehicles. This one. Till this first and second zone, this one is for normal operation of induction machine. Right? So this is all about the performance of an induction machine for this module, that is sterilized AC motor drive. We will be meeting in the next video session while continuing this module. So thank you for now.